continuing on with class 2. Here is a new topic, or another topic. We did constant acceleration there in the previous video, but now we're going to also cover this relative motion and dependent motion. And so you can see even in Johnston, they kept this in the same section. This is 11.2c. So relative motion is pretty easy when you first deal with it, right? Because you already kind of know this stuff, right? It's deceptively easy. And it's going to, by the way, this topic is going to continue through the semester of relative motion. When we deal with rigid bodies, this is going to be really powerful and interesting. That's how we're going to account for relative positions of points on a rigid body. So this is something we're going to deal with again and again, but just in a straight line right here. So it doesn't need to be a vector, right? We have, if we want to find the position of B and we know it, and we know the position of A, if we want to find the difference between them, we say we want to find the position, the distance is x, B slash A, right? So this is, and we say it as B with respect to A. And so it's B as a subscript x, B slash A right here. And we will often say, well, that is, if we want to find the position of B and we know the position of A, all we need to do is add the relative position of B with respect to A. And there's a couple of important things to note here. It's almost like a subscript math. You can think of it, right? That we need A, and if we're going to do something with A, we have to have this position where here's A, and then this is going to be with respect to A, and that's going to get us B. And if we take the time derivative of this equation 11.9, we end up with equation 11.10, right? Because if these things aren't changing with respect to time, then we have the velocity, right? We can get the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. And this has a physical meaning that you should be familiar with if you're in a car and if you're driving in the left lane and passing, and you go by somebody, right? If you're passing by, I guess to me, this is my left, but your things anyway. As you're passing the person, it could appear that you're traveling like maybe 15 miles an hour faster than them. If you're going 75 and they're going 60, it'll look to you as a driver or passenger or whatever, as if you're going 15 miles an hour faster, and that's your relative velocity. That would be VB with respect to A. So if you knew let's say that you are A, right? Let's say somebody's passing you, right? And you're driving 60 miles an hour, and you see somebody and they go past you, and it appears to you as if they're going 15 miles an hour, right? Faster. So then you could say, they must be going 75, right? So you are A, you're the reference, and here is the B with respect to A, and then here is this is the result, right? You could find. So it's pretty intuitive, right? I decided to flip around who was going faster because this could also be a negative number, right? Which isn't the case if you're like passing someone. But I'd rather have it like, keep in mind that the second term right here is the basis, right? It's the thing that we're comparing to, and it's the one that's in the denominator of this. And then we have the same thing. We take the derivative of it, and we can get acceleration that way. Now, this relative motion, we have relative motion, and we also have dependent motion, right? And dependent motion is, the most common example that we'll deal with are pulleys. And we have a procedure to go through there. That just means, like, if this thing moves, if B moves, A is forced to move. They're dependent on each other. There's something that's linking these two things together so that they have to be true. these dependent motion. And like, it could be as simple as having just one simple cable and moving the thing. Our problem with the pulley problems is there could be lots of different pulleys involved. Now, even though this might be, this one is going left and right and this one's going up and down, it's still treated as like a one-dimensional problem, right? Because they don't go out of their relative positions, right? They get stuck together. They're stuck together. So we could just think of it as being a one line that they're moving through. And the procedure to work through a pulley problem is to first create a datum, right? Some reference for each of the parts. In this case right here, let me see, I'm going to make sure I'm saying all the things that I want to include. If we're doing a pulley problem, we set up some type of local coordinate system onto the thing. And I'm going to use S. You can use any letter that you want here. So we could say that this guy right here is SA, right? So that just means it's just a position. Instead of using X, right? I don't want to mix X's and Y's together here. We're just going to say S. And we have this distance right here, that's going to be SB for a coordinate. So we're going to say that direction is the positive direction, right? So, and it's just for the time being, doesn't matter. So we define the datum, and from that datum decide what is plus and minus. So plus is that direction, and plus is this direction for B, right? Then we write out the expressions for the length of the cable in terms of the position coordinates we've just created. So noteworthy is that if we're going to have the length of the cable, it's going to be this guy plus this little arc right here plus that length. We're going to find out that arc doesn't really matter to us, but we will include it for a little while in some of the examples, right? And I'll show this in operation, right? And then we want to take derivatives of the expressions that we read out in part 2 right here, right? And take the derivatives of them again, and that's going to give us velocity relationships and acceleration relationships if we take the derivative of them. So let me just, as a simple matter, let me write out this step 1. Right here. So this is 1, 2, and 3. So 1 was to put in these datums right there, and then 2 was to take the length of this thing. Well, what is the length of the rope? Well, it's going to be L is going to be SA plus SB plus, and I'll write 1/4 of the pulley. That's the length of this rope. So now 3, take the derivative of that. Well, does the rope ever change? The length of the rope ever change? No, so it's 0 taking the derivative of this. This guy is going to be VA. This is going to be VB. And taking the derivative of this, does that length ever change? No. So it's 0. So here we have a relationship. 0 equals velocity of A plus the velocity of B. But that means that the velocity of A is going to be equal to the negative velocity of B. So if this thing is increasing in its positive direction, this guy is decreasing in its negative direction from that, using those reference points. Makes sense, right? We could also say this right here. So writing this out, I didn't leave myself a lot of room. I'll come up to there. So velocity of A is equal to negative times the velocity of B. We could take the derivative of that and find the acceleration of A is equal to the negative acceleration of B, which is pretty straightforward. In the book, there's they have a sample problem 11.7, so I've included a link in my notes that you can go to see that video. But let's work through, and I'm calling these examples, but we'll do a full example in another video. But here is the scenarios. Some scenarios that we could go through first to have a little bit more complication right here. So to start with, on this first one right here, and I'm going to quickly change this around, but on this first one here, what we could do is we're going to include all of these small little pieces of the thing, right? But for now, and then we're going to quickly recognize that they're not necessary, so we could take like a little shortcuts, but in the beginning we can take this, right? So I'm going to take datum from up here, and so here's my first datum. Actually, they're drawing them on there for us. And they decided to use x, right? So here's xa, and then here's xb, and it's coming from this datum up here. And we'll see soon that we don't have to have datums all the time. I want to measure a couple extra stuff. So let me say this distance right here, we'll call this h1 to get down to there, right? And maybe I'll make this distance right here, I'm going to say he's going to be h2. And then this arc, I'm going to end up calling him CD, and then this arc is going to be EF. So let's figure out the length of this entire rope right here. It goes up here, down there, back up there. It's one single rope. Let's find him. L is going to be, well, let's see, starting here, just marching through, this is going to be XA minus H1 right there, right? Because we start from there, so this length right in there. XA minus H1. Now marching through the rope, we go to CD, which is really just 1/2 of the pulley diameter. We don't know the pulley diameter, but we know that that's going to be, if we did, that's what that arc would be. That'd be 1/2 the circumference of it. Plus, okay, so now we're going to come from here down to here. And we're also going to subtract out this guy and that guy from here, right? So it's going to be plus XB, right, all the way down to here, minus H2, right there. Okay, so now we have this length from here to up all the way there, but now we have to subtract out H1. And then lastly, we have this length right here, which, okay, so now I need to go down to the next line. We need EF, right? That arc. And now we need this length right in there. So we go plus XB, but minus H2. And so that's the length of the rope. Well, there's several things we don't know about the rope. We don't know this distance. We don't know that distance. We don't know these. But let's move them all over, right? We can move them all over to the side and lump them together, right? So we could say that L minus CD. Well, let me go first with this guy right here. Let's go L. I'm going to move this guy over, so it's going to be plus H1 minus CD, and plus H2 plus H1 plus EF plus H2. Oh, it should be minus EF, right? We jumped him over to the other side. Is going to be equal to XA, and there's an XB and it's plus 2XB. We could lump all these together and call that C and say that it's equal to XA plus 2XB. Well, if we take the derivative of it, we're going to have 0 is equal to VA plus 2X, oh, not X, VB. So therefore, VA is equal to negative 2 VB. So if this thing moves at 3 meters per second, this one's going to be, and going downward, let's say it's going downward, then this one's going upward at 2 times that, right? So what did I say, 3 meters per second? I think I did. So then this is going up at 6 meters per second. A is going to be going twice the velocity, twice the magnitude, but in the opposite direction. And you can also do the same thing here with a second derivative of this and say the acceleration. That's the big idea. Now, we didn't really need these right here, so we're going to abandon them. We're just going to toss them away and just write out the length of the thing. So one way of doing that is like I could just take this line right there, right, as my datum. Because that length never changes, that length never changes, what have you. So I could have go down right here. So instead of what they're showing on here is XA, I could show that as XA right there, right? Because this length never changes as well. And that length never changes. And then over here, here's my XC instead of the way that they're drawing it. And then right to there is where I have my XB, right? It's a shortcut, but it's going to save us. We just start thinking of it in those terms. When you practice the problems, it'll become natural to you. But okay, so those are all the positive ones. So if I want to get the length of the thing, I just say, oh, wait, 1, 2, right? So there's 1, 2 that are in between there. So I'm going to say the 2XA. 2XA, right? And then we'll see that this length, those two, we're going to have plus 2, and that's XB. And then we only have one of these, XC, one of them. So take the derivative of it, 2VA plus 2VB plus VC. And we note that in this case right here, there's 3 things that can be happening. There's 3 variables. So in order to know what the velocity of A is, we need to know velocity of B, and we need to know the velocity of C. Sometimes they might say, well, we know that the velocity of C with respect to B is this amount, right? That's from the previous section on this. What did I do with that? Right? That's from the relative motion, right? We might have that relation, and then if we know that relation and then we know one of the velocities, we could find the final one. Then we have enough information to solve it, right? So be aware. That's something that we can also do. So here's the acceleration. Take the derivative of it again. We see this and 2AB and then plus AC. So here's the acceleration relations. Now, if we have multiple cables that are taking place, and let's say A is the end of a cable right there, what we could do here, and you're going to have to write these in carefully right in there in little gaps. We could say that here is, I guess I'm going with the X's. And right here is going to be XB. And right to here is XC. Right here is XD. And now we can figure out cable length 1 is going to be XA plus XB. There, right? Oh, no, 2XB. That's true, 2XB. I should look at my notes. Yeah, so here's this one and that one. There's 2 of them, right? So that's a single cable right there all the way up. Now, let's take for the next cable right here. L2 is equal to, well, here we're going to see that we have to get this, right? So this little cable right here is going to be XC minus XB. This is that little length right there. And now this length right there is xc, right? So we know that what we have is negative xb plus 2xc. Now let's go for the last cable. That's this guy right here, and he's almost identical sort of arrangement. So we're going to say that this is going to be xd minus xc is what that length is. And then this is just going to be plus xd. So we have a negative xc plus 2 times xd. Did I get that right? Yes, I did. Now take the derivatives of them, right? And what we're going to find out is right here, we're going to have VA is equal to negative 2VB. We're going to find, did I do that right? Yes. We're going to find that VB is going to be equal to a positive 2 times VC, right? Because there was negative there. And then we're also going to find out that VC is going to be equal to 2 times VD. Now, if we plug all of these in here, right? If we say, okay, here's V, let's plug that guy into there and plug him into there. We can say that VA is going to be equal to negative 8 VD, which means that they move in opposite directions, which kind of makes sense, right? So if we're pulling this downwards, this one's going to go up. And by the way, they might have asked for E, but we know that VD and VE are equal to each other. So we could just substitute that in there. But we know that A is going to have to move a lot faster than D, like 8 times. Or we could say that VD is moving 1/8 of the speed of VA, right? So these are dependent motion problems. Like I mentioned before, we might also put in here, like in this case, because we have 3 degrees of freedom in there, we might want to enter in one of the relative velocity positions or one of the relative acceleration things. We can also combine it with the stuff that we did at the beginning of the class, where we used some of our constant velocity relationships with a much more complicated arrangement. But the important thing is to think our way through. Now, one last thing that I think is good, because we look at these dependent motions and we think, oh, why don't we just always call them pulley problems? I just want to give you an example. I don't use it very often, but like, let's say that we had like a little dude right here, and there's a flashlight right here, and it's shining out, and what we're going to find is his shadow right here up on the wall. I'm going to draw him like that right there, right? If he moves in a different position right here, right, from there, this shadow height is going to drop down. That's a dependent motion problem as well, right? If we were trying to measure the height of that shadow onto the thing, all of a sudden now it's going to be, lower right there. But there's going to be something related to the two, right? So it doesn't have to necessarily be rope, right? That's causing that. It's just really the example that we're using. We're just looking at some exterior thing that's a rule that binds the two things together, and we see that they're dependent. Like one motion depends on the other, and it doesn't necessarily always have to be a pulley, a rope. But there you go. There's my introduction. And how long did it go? 25 minutes. Takes too long. But I think it's good to maybe have this video for you to go back if you get confused in class, and that you go back and look at this thing. I like the idea of conservation of rope. So I'll do an example in the next video here. Let's see. Will I do 2 examples? I might do 2 examples. Yeah, I think I do 2 examples. So I'll do two more videos for class 2.